car accelerates uniformly from rest to a speed v in t1 seconds. It continues at this constant speed for t seconds and then decelerates uniformly to rest in t2 seconds. The average speed for the journey is 3v/4. Draw a speed time graph for the motion of the car. So we're drawing speed against time. Speed is the magnitude of the velocity. That's v without an arrow. So for the first part, the car accelerates uniformly from rest. That means its initial speed is 0. And we're assuming that its time is 0 initially. It accelerates uniformly. So that means that the speed time graph is a straight line. That's the only situation we'll be dealing with in the course. So it accelerates uniformly for t1 seconds. So for a time of t1 seconds, it accelerates uniformly to reach a maximum speed v. Not this v, this is just a generic v, just the name of this axis. We're given that it continues at this constant speed, that's a constant speed v, for t seconds. So for t seconds, it continues with a constant speed v. So the velocity time graph is just a horizontal line. Its slope is 0. The acceleration is the slope. The slope is 0 means the acceleration is 0. It then decelerates uniformly to rest in t2 seconds. So decelerates uniformly means it has a negative acceleration. So the slope of the velocity time graph for this section will be negative. We'll have a line with a negative slope. So what this slope is, I don't know, but we're given that it decelerates in t2 seconds. Now we're given that the average speed for the journey is 3v/4. So what is average speed? Average speed is distance traveled divided by time taken. Time taken to cover that distance. The distance traveled is the area under the speed time graph. This purple area here. You can think of this as the integral of v of t with respect to t. We just multiply the speed by the time. We can see it from this actually. If we multiply average speed by time taken, we get distance traveled. If we multiply instantaneous speed, that's the speed at any time t, that's the height of this graph at any time t, times dt, which is an infinitesimal amount of time that elapses. Then we get the infinitesimal distance covered dx, x or ds if you like. S is what's usually used for distance. So that will be v of t times dt gives ds, and then we integrate or sum all those rectangles if you like. So it's a rectangle of height vt and width dt. You probably know that from basics of integration, but we won't be actually performing an integral here because this area is quite easy to calculate. It's made up of two right-angled triangles and a rectangle. We're given in the question that the average speed is 3v/4, where v is the maximum speed of the car. So let's just explore this equation here. It'll help us to answer part 2. So the distance traveled is this area, so it's the area of this triangle plus this rectangle plus this triangle. What's the area of this triangle here? Well, it's a right angle triangle, base t1, height is v, so it's half the base by the perpendicular height, half t1v, plus the area of this rectangle, which is just got by multiplying the two sides together, v times t, plus the area of this right angle triangle here, which is half the base by the perpendicular height, half t2 times v. That's the distance travelled. And what's the time taken? Well, we just add up the 3 times. The time taken is just the base of this curve. That's t1 plus t plus t2, and that equals 3v/4. Now what we have to do in part 2 is find t1 plus t2 in terms of t. So we have to actually somehow get t1 plus t2 out of this, assuming it's possible to do. Well, it must be possible to get t1 plus t2, otherwise we wouldn't be asked this question. But there's no reason why it always has to be possible, because it might only be possible to get something like, say, t1 plus 3t2, or some other combination of t1 plus t2. But apparently we can get t1 plus t2. So let's see what happens here. We can divide both sides by v. So just divide the numerator of the left hand side by v and divide the numerator of the right hand side by v. V's cancel. And then cross multiply. So we've single fraction equals a single fraction. So 3 times the denominator equals 4 times this numerator here. So we have 3t1 plus 3t plus 3t2 equals 4 times a half t1, which is 2t1, plus 4 times t plus 4 times a half t2, which is 2t2. And somehow we should be able to get t1 plus t2 out of this. We should be able to isolate t1 plus t2. So let's bring all the t1s and t2s to one side. So we have 3t1 minus 2t1, that's just 1t1. We have 3t2 minus 2t2, that's 1t2. So we do actually get t1 and t2 in this form, 1t1 plus 1t2. And I bring t's to the other side. So we have 4t on the right hand side, minus 3t is 1t. So it's actually t1 plus t2 equals 1t. So that's what we have to do. We have to get t1 plus t2 in terms of t. It's actually equal to 1t. If a speed limit of 2v over 3, that's actually 2/3 of v, 2/3 of this distance here, were to be applied, find in terms of t is this distance here, the least time the journey would have taken, assuming the same acceleration and deceleration as in part 2. So let's just look at the velocity time graph for this new situation. Now, the speed limit is 2v over 3. That's 2/3 of v. So there's a lower speed limit. We're given that the same acceleration and deceleration applies here. So what that means is that for the first leg of this journey, we have a line that has the same slope as this line here. But it gets cut off, not at v, but at 2v over 3. Then we assume that the object is continuing at constant speed for a certain time. It won't be the same as this time here. And the object decelerates with the same deceleration as for the last leg of this other journey in part 2. So this line here has the same slope as this line here. So you can see that this speed time graph is not as high as this one. But what we do know is that the areas are the same. So this area here will be the same as this area here, because the same distance is covered in both situations. It's just that the speed limit is lower, that's all. But we want these areas to be the same. So if the height of the graph is decreased, then obviously the width of this graph has to increase. So the time taken is actually going to be longer than for here. The time taken here was just this distance. The new time taken is this distance here. This is the new time taken for the entire journey. Now I'm going to call the times taken for this journey T4 for the first leg, T5 for the middle leg, that's when the car is travelling with constant speed, 2/3 v, and T6 for the final leg. So what we want is the least time the journey would have taken. So we want to calculate T4 plus T5 plus T6. Well, T4 plus T5 plus T6 will be the exact time to cover this distance here, this shaded region, which is the same as this. So we want T4 plus T5 plus T6 in terms of t. Well, let's look at this distance here. we can equate it to this distance, which we worked out in the first part. And by equating these, hopefully we can answer the question. Well, there's going to be more to it than that. We'll be using this substitution from part 2 as well as a few other substitutions. We have to use the fact that this line here has the same slope as this line, and this line here has the same slope as this line here. We have to use those facts as well, because the accelerations and decelerations for the first and final legs of the journeys are the same. So let's start by looking at the two areas. Well, what's the area of this here? Well, it's the area of the triangle, which is a half t4 times the height, which is 2/3 v, plus this area of the rectangle is t5 times 2/3 v, plus the area of this triangle here, which is half the base, a half t6 times 2/3 v. Let's move it down here. So this area here equals this area up here, which we got previously. That's a half t1v plus t times v plus half t2 times v. What you can see here is that v is cancelled out all the way across. I'll just do some simplifying here. We can cancel a few things here, and I'll just rewrite this down here. Okay, we have a half t2v at the very end here, so that's a half t2. So that's just breaking down some of these fractions. Now, we need to try to relate everything back to our original situation, which involves t1 and t2. So we need to replace t4, t5 and t6 with t1 and t2, and ultimately we can replace t1 plus t2 with t. So we're aiming to get everything in terms of t. We'll be looking at this expression here. So what can we do with t4? Well, we use the fact that this line here has the same slope as this line here. So that means that this triangle here is similar to this triangle here. Angles are the same. Okay, the acceleration is the same. So the slope of this line is the same, which means that these two triangles are similar. They have the same angles. You know, this angle here will equal this angle here. The slope of the line determines this angle. So these two angles are the same, and they're both right angle triangles, of course. So if the triangles are similar, that means the angles are the same, then sides are in proportion. So we know that v over t1 must equal 2/3 v over t4. v over t1 equals 2/3 v over t4. So that means that t4 is 2/3 t1. Okay, that's just by dividing corresponding sides. The v and this side are corresponding, and the t1 and this side here are corresponding. An even quicker way to do this would be to see that the height of this triangle here is 2/3 the height of this triangle, which means that the base of this triangle t4 is 2/3 the base of this triangle here, 2/3 of t1. So that only happens for similar triangles. So these angles here, represented by the dots, have to be the same. That means the slope of these lines are the same. So t4 is 2/3 t1. Now similarly for the other triangle, we can see that t6 is actually 2/3 of t2, because the height of this triangle here is also 2/3 the height of this triangle, which means that the base of this triangle, t6, is 2/3 the base of this triangle. So I plug this 2/3 t1 in for t4. So I have it here, and 2/3 t2 is plugged in for t6. So I write out the left hand side, making those replacements in. That's what you see in brackets. Just copy out the right hand side. Now here we have a third times 2/3 t1. That's 2/9 t1. And over here we have another 2/9. So we have 2/9 into t1 plus t2. Now that's good, because we can replace t1 plus t2 with just t. What's left is 2/3 t5. On the right hand side we can factorize a half out of these two terms, so we get a half into t1 plus t2. That's good as well, because we can replace t1 and t2 with t from the previous part. We want to get everything in terms of t. So now you see that what we end up with is an equation in t and t5. So let's get t5 in terms of t. We want to get t4 plus t5 plus t6 in terms of t, so we'll have t5 in terms of t here. We have a half times t, this thing was t I said, plus 1t, a half plus 1 is 3 halves t. We have 2/9 t here. So we just calculate 3 halves t minus 2/9 t, or 3 halves minus 2/9 all times t, divided by the coefficient of t5, which is 2/3, and you will see that that is 23 over 12 times t. 3 over 2 minus 2/9 all divided by 2/3 is 23 over 12. So now we can get t4 plus t5 plus t6. t4 is 2/3 t1, t5 is 23 t over 12, t6 is 2/3 t2. Now we can write this first and last term as 2/3 times t1 plus t2. But then we see that t1 plus t2 is just t, so that's working out well. So we get 2/3 t plus 23 over 12 times t. And there's our final answer. That's t4 plus t5 plus t6 in terms of t, where t was the time taken for the car moving at constant speed for the journey of part 2.